Hi everyone, welcome back from winter break. In this video, we will be discussing the engineering design process, our design alternatives, and our virtual prototypes. So let's get started. We underwent what is commonly known as the engineering design process, or EDP for short. The first step in EDP is to communicate with our customer to see what it is that they want us to achieve. In your case, this might come in the form of a problem statement. In our case, we were asked to build a functional model of the launch and recovery system that you saw in our previous video. We then created a list of customer requirements, followed by a list of engineering specifications, which are measurable tests to determine the success of fulfilling the customer requirements.
When coming up with design solutions for the launch and recovery system, we utilized an iterative approach. This meant that rather than gathering up together and coming up with solutions straight away, each one of us individually designed the potential solutions for the large system. We then gathered up together and analyzed all of them for their advantages and disadvantages. Some of them you can see on the board here. For example, Bring It Around Town utilized the 120 degrees rotating base, whereas the 3-point arm utilized a completely different approach. 3 independent links, each one operated using an individual stepper motor. However, what we thought would be the best design going forward was the Too Cool for School. 2 independent links, 2 separate stepper motors, and 2 linear actuators. However, thinking about it further, we decided that every solution had something to offer for the final design and for each of the customer requirements, and that the best way going forward would be to combine them and come up with our first virtual prototype, presented here.
When analyzing our first virtual prototype, we realized that our current model would not have the sufficient reach that a real launch recovery system would. On real launch recovery systems, the research equipment needs to be lifted a certain distance up from the dock and be pushed out a certain distance away from the boat in order to be able to deploy the research equipment properly. In order to make our model more accurate, we developed what's known as a telescoping arm. Telescoping arm you can see right here. This will give us the reach necessary when we need it in order to deploy the research equipment properly. As most of you know and probably dread, engineering requires the use of different types of mathematical analysis. And in this case, there was no exception, we had to as well. We used what's known as sum of the forces analysis, where we broke up this model into a telescoping arm, second link, the first link, and the base. By doing so, we were actually able to find out that this first linear actuator would cause link 1 to twist in a way that would break our entire model as soon as it would start. To remedy this problem, we had to figure out how to distribute that force in such a way to mitigate this problem from happening. We did that by changing the geometry of link 1 just a little bit and bringing the linear actuator on the inside that you can see right here. This model that you see right here is actually our final virtual prototype, and it shows a little bit more of the aesthetic features that we're including, such as the acrylic panel, the wood links, the metal components, and the plastic components we are 3D printing.